Hello boys and girls. In this video I'm going to go through a script that effectively aims at brute forcing private keys and checking them against the funded addresses on the Bitcoin blockchain, i.e. you can still, with enough time, you can steal all the Bitcoins. I start by showing you how that looks if I execute it. So this is the script, it's called here from Python. I hit enter. It runs through all the funded addresses. I'll show you how to get to those in the script. It like lists all the addresses up to a certain funding amount. I've gone down to I think 9 Bitcoin, so we have to wait. Now here this is 12, 11, 10. So now he has finally loaded all the addresses, and so this is the lowest one with 9 BTC. And what happens next is that he generates a bunch of private keys in the background and then checks whether or not this address is funded by comparing it against the list in a efficient sort of way. What I do here is also I print out whenever there is a match to the last 4 symbols or characters of the address. So after just a short time there will pop up some addresses, some matches, and of course once you get a perfect match, once you have a match of addresses that goes over all, I don't know how many characters, then you have access to that wallet. Okay, so here you see already some matches. Here these are addresses which end in 68F6. This is one that is generated with a private key. This is the private key in decimal. This is the private key in base 58 check format, i.e. Bitcoin private key. And here is an address that is currently funded on the Bitcoin blockchain, and the last 4 characters match here, right? So this, like you see, generates a bunch of keys, it checks against, and these are all these matching ones. So for example, okay, I will stop this here, okay? You get how this is intended to work. Let's look at this. So this has a matching of JXZZ. We know the private key to this generated address, and this is a funded address on the Bitcoin blockchain. I can show you that it's funded by just copying it, and let me go to blockchain.com. This is some 99 Bitcoin address. If I now add the address that we just copy pasted and look at it, then we will see, you see this is an address which happens to have 73 Bitcoin on it. Of course, our match is only very partial. So here we have just found a key that matches with the last 4 symbols, and only if we would have a perfect match, then we would be able to steal all this money, right? Obviously, in practice, this script doesn't work to steal any money because you have a chance of 10 to the power of minus 60 or so to find any address in the first place. So it's practically speaking impossible, but in principle, you can use it, and also you can use the script to generate, for example, private keys that correspond to addresses that have some vanity feature, right? You can say, hey, I want to have a Bitcoin address which ends in sexy, and then you can generate random private keys until you find one, and then you have a custom address where you can dump your funds to. Okay, so for some background, first, before we go through this like 200-line Python script, similar thing, what I do is also done, for example, on allprivatekeys.com. This is a website which, like, for every like private key that you might want to consider, looks up the funds on the blockchain, and it computes for you all the addresses for this key on various chains and stuff like that. It's basically a gimmick, the same gimmick that I did in doing this video and have done in the last two videos. Okay, so what I do here is relatively efficient. I mean, apart from me using Python, which is never very efficient. But it's efficient in the sense that I don't actually interact with the blockchain, but I just use a CSV format list of all funded addresses together with their funds in an ordered format. If you're interested in that data, it's on Bitcoin, the Bitcoin forum, the main one. You can find this being posted. It's called Addresses Lois Club, where every other day all funded addresses, a snapshot is taken and it is updated here. And so if you want to run the script locally to test it out, then you have to take, in this case, this one here, which says latest. This is a list of all addresses with balances. And there is a lot of funded addresses on the Bitcoin blockchain. So you will have a problem just loading this this file to RAM or something like that. To actually do what I do in the script, and there's some more smarter streaming of this data, and I do fingerprints so that I can actually work with this huge amount of addresses, as you will see in a second. But in any case, if you click here and download it, I think it might be a few gigabyte large. This is basically just a CSV list with the addresses and their funds. Okay, this is probably the last of these like blockchain themed videos in the near future, but in the last 2 weeks I already did 2. I mean, in the past I did a bunch of like elliptic curve stuff and these kind of things, but I did the how to match a secret integer to a private key and to an address, and talked about the mechanism and algebra of the elliptic curve as used on these chains. So these are these 2 videos, and in this video I will code up like 6 functions or so, and one of them is the secret to wallet input format. So I will not explain this in this video. If you want to know how to get from this private key, aka the secret, to the base 58 and why is base 58 in the first place and so on, this is the wallet input format version. How this projection works, or at least how to go from the integer to this base 58 version, I explain in that video, and I make use of this also in this video. Okay. Yeah, okay, I guess this is like me opening this. This is the function that I coded up that maps from this integer to the width. Okay, by the way, subscribe to the channel if you have not already done so. Okay, so with that said, let's step into the script. Well, first let me run it again, okay, with some other configurations. Okay, I step a little bit into the future. For example, I can also like tune a few parameters here. I can say take only addresses which have at least 999 Bitcoin. I can also go to 1000. There is nothing magic about the 9s. And or print all print all the addresses that match with the last 3 characters. Okay, this is just the printing, and this is just where I have this data set stored, as I just said. And this is whether or not I want to generate random keys or just want to start at 1 and go through all keys. And so if I do that, if I run it again, then the loading will be shorter because he only considers all very rich Bitcoin addresses, and it will find much more matches because I only require him to find the last 3. So let me break this again. So yeah, and as for like for practical considerations, like on this machine, this is just a MacBook Air. If I set it to 6, for example, then I have to wait quite a bit before I find some matches, although it works in principle. If I go to 7 or 8, then I'm not even sure if I find 1 match per day. So there you can see how like hard is it to find any address. Now I set it to 7, and it's not going to find any match for the last 7 characters even. And as you can see, the Bitcoin these addresses, how many characters do they have again? Like around 40, I suppose. Yeah, every 1,000 or so tried addresses, he will make this print statement and tell me how long he's ran. So since this doesn't really work to actually steal any Bitcoin, which you shouldn't do anyway, you can nevertheless use it for various things, like you can find addresses. For this, however, you don't need the funds. But for example, you can also, like, if you have this dataset downloaded, you can also find addresses by, find like your address, for example, by just a fraction of the information. So for example, if you know that the characters ABC are in sequence in some address of interest, maybe your Bitcoin address, then you can use the script also to find your own complete address for whatever reason you might need that. I mean, maybe you have your private key stored at your mom, and this is your way to find your own address. Whatever. Okay, so yeah, I already pointed you to these various links. I already discussed practicality considerations. Of course, as always, don't actually use this particular script because, I mean, I've coded it up for fun and I've refactored it a bunch of times, and so don't use any crypto that I have not taken too much care to ensure that it's safe, right? So if you have some blockchain project running or anything, refer to the like established libraries. By the way, I recently found out that, for example, what's it called, Electrum Bitcoin wallet is also a Python project actually. So there is a lot of cryptographic standards and I suppose good practices, I would expect. If you're interested in some Python routines, apart from looking at Python code for some projects, you can just check out this Electrum wallet implementation. It's on GitHub. Okay, so for this video, I don't use all that much from the standard libraries. I have, again, some hex conversion. I use the zip library for loading of this file with the finite addresses, right? I import the time library just for printing the time, as you've already seen, right? Or for printing how long I've ran the script. And then there is the hashlib, like the SHA function from the hashlib library, as I've already used it in the last two scripts. SHA-2, you gotta need it. I have many videos on SHA-2. Also a bit level implementation of SHA-2, by the way, on this channel, if you're interested in that. And then the elliptic curve digital signal algorithm library. Here I need just the curve that is used in Bitcoin, as explained in the last video. And then I found, like in the last video, I already showed you how to go from the secret, just integer private key, to the addresses. Some script, probably not very efficient. I also found last week some guy's library that implements the same thing, and it also does the newer SegWit format. So it has like 5 different address formats. So I would recommend just using his stuff. And I have tested it against mine, so everything works out fine. Under the hood, this Bitcoin addresses library also makes use of this thing to use the elliptic curve to match from the secret to the addresses. Okay, these are the imports. Then here are some, again, Bitcoin particular elliptic curve features. So the smallest key is 1, right? Like per convention, the 0.00 would also be a valid point on the elliptic curve, but by convention is excluded from the Bitcoin blockchain. Then the maximal key, I think this is technically correct. I always get a little bit confused on whether the keys might be even more restricted than just the order of the elliptic curve. But I think technically there's no problem with that. So in any case, this is the biggest key we are considering here, which is just the order of the elliptic curve, maybe -1. I think if you remove that and use the biggest, like if you use the order actually as a private key, then it throws an exception. Okay, but this is really a very technical detail. Then the name, as I already pointed out, of this file that we're going to load, and then some configuration that might be particular to what you want to do. It's a configuration struct. As you have already seen, I can configure down to where I want to load addresses for this comparison sake. For example, I can go down to 0.1. Oops, no, wrong side. So I can go down to 0.1, and then it will load all funded addresses in this snapshot that have 0.1 or more Bitcoin. So this is a lot of addresses. It will take forever to actually load. And of course, then you compare against a bigger size of fingerprints. By fingerprints, I mean the last characters of the address, which in turn means one iteration takes longer, but I mean, depends on what you want to achieve. I suppose if anybody would really put in the work to steal Bitcoin, then this person would not be interested in stealing 0.1 Bitcoin. If there's a chance to steal 1,000 Bitcoin. Then, okay, this is this printing time, 1,000 seconds to, 1,000 checked secrets to print. This is just the relative path where this file is lying. And then whether or not I want to use a random seed, right? So, for example, let's say let's go up with this again and put this down to 3 again, right? So it will have a lot of matches because only the last 3 must be matched. If I turn the random seed off, then it will not use in the script a random key, but instead he will run through all private keys starting with 1. So 1, 2, 3, and so on and so forth. So if I do that, then we will see, right, he's already done, like he already loaded he had already loaded the addresses, and then he tries all to fold his matches. And here you see, for example, the private key for this private key. This private key is actually just the private key number 667. So it's a very small, insecure private key. Insecure for the reason that if you iterate through all private key, it pops up early. And he tries to match the last 3 characters, in this case RTC. This is the address for this private key, and here we have again the funded address, as I can confirm here. So this is some huge address. All right, so this has 5,000 Bitcoin. Okay, so that's how it works, right? Since like pages like all private keys already started at the start, it's maybe not so interesting. So I will just use random numbers. For example, the seed 0 is okay. Okay, so this is the configuration. This is what the script does. Now I'll give you a general overview on the functions that we have here. So here, this is the function that generates just the next secret. I pass the index, like the nth iteration, and it can use it. If the random functionality is on, then it pops just one random number in the interval between 1 and the order of the elliptic curve, and returns the secret. Otherwise, the custom function I have implemented here, I mean, you can do what you want, right? But the custom function is here, just take the nth, in the nth iteration, take the nth number, take the number n as secret. Okay, then there are some sanity checks and return it. Then this is the function which turns the wallet import format key. There's some string where this long string, it's ugly one, like these are these private key encodings. Take this with, use this library that we imported above, right? This was this wallet library here. And then this creates this class called wallet. So it creates an instant, and then you can look into this. There we find just as member variables these addresses. So this is, for example, the standard uncompressed address. We have discussed the uncompressed and the compressed address in the first video in this video in some detail. And then also like this, you know, the free in front, and then SegWit and whatever you have on the protocol, on the Bitcoin protocol. Okay, then the fingerprint function, which just takes the last n characters, right? You pass a word and you take the n characters. This is defined in the config above. And I take the last ones because the first ones might have different features, like one starts with 3 and one starts, the SegWit one starts with BC, right? The address formats are different. And so the looking at the last characters is like treats them more on equal footing. Otherwise, if I would, for example, take the first n characters, then since there are so many addresses with BC, there would be much more matches, and maybe more matches than the ones that start with a 1 and so on. Okay, so again, this is like a particular aspect of the protocol, that the addresses have start with some special characters on the format by convention. And so we just take the last ones and we consider this our fingerprint. The fingerprints are what we match against, and if the fingerprints match, then we actually check whether or not it's the perfect fit. Okay, then the funded address stream, this is what reads in this file and eventually yields one address after the other up to the fund level. Okay, I will discuss this in a moment. Let me skip this for a second. Then a secret with, this is the one where I already said I have explained this in the video 2 weeks ago, and I will not discuss it yet. Here I compactified it a little bit, but more elaborate discussed version you find here. So this was this video. This is exactly this function, but here I have written it down a little bit more nicer, and here I just squashed it together. And then there's a unit test that checks whether the first key, which happens to be this one, you know, so it ends with DF. You can also probably see that. Yeah, here, this is the first, like this is the all private keys. As I said, this is the first private key, right? It ends with DS. This is exactly the one. And so I just check with this test, with this assertion here, that this implementation is valid. Again, don't use this implementation for anything you actually need to use in any project where money is involved or which needs to be secure. Okay, and then the script looks as follows. First, we generate a stream with all the addresses that have funds as we like them. Right, this is this. Then we take the fingerprint, this is the fingerprint function of all addresses in the stream. So we have this list of last few characters. This is what we are going to use to match funded addresses against it. Then here we have a custom function which does exactly that. So here is here's this list of all fingerprints that have funds, right? And so here, if you pass any address, it's going to be the addresses that we are generating on the spot. Then you create the fingerprint, the last n characters. Then you go through the list of all fingerprints that are funded, and just test whether or not it says yes, this is the same, and then return true, otherwise return false, right? So this checks whether or not all the fingerprints match. And with this function, we go into the main loop. This is the rest of the script. It's also very short. Okay, here we start time just for benchmarking, has no implementation relevance really. We loop through all numbers, right? So this is like some huge number that we're never gonna reach. This is a stream of all natural numbers, and we go on. We see the first one, an optional printing function, right? Every epoch it tells me how long it already ran. Then it takes this index and generates the secret, right? Again, if you have a seed on, then it will just return a random secret, random integer number, that's the private key. Otherwise, if you have no seed on, if the seed is set to -1, then it will return just the nth private key, which is n itself, right? And this is then just the identity function if you just want to run through all the private keys. Then there's this secret to with function. You have the with corresponding to the secret. Then you have this function with this wallet library that returns the 5 addresses. And then if any of the fingerprints of these 5 addresses match one of the funded addresses using this fingerprint matching function that we have here. Then analyze it further and print some stuff, right? So we again, in that case that the fingerprints of some match, then run through all the. I mean, this doesn't happen often, so we can like it's not so bad if we load again the funded address stream because we want to take a closer look. We take the funded addresses again. We for every of these addresses we compute the fingerprint, and then we'll go through the 5 addresses and we check, okay, for sure if the addresses are equal at all, if we like found perfect match, then the length of the address must be the same, right? Not all addresses are of the same length, right? As you saw here, like this compressed format address is much shorter than some of the ones that we free is probably much longer, and then the SegWit ones, right, also use different characters and so, as you see here. So this is a minimal check that the lengths of the addresses are the same, and in that case, if also the fingerprint is the same, then we print it out, and this is the printout that you saw here. Sadly, I cannot really scroll down anymore. Then we make this print statement. This is exactly what you saw here all the time, right? In case there's a match, print what the secret is, print what the width is, and print what the addresses are. This is what is done here. And finally, do a check for a perfect match if the address is, if the address here, one of the like 5 random generated addresses, is actually one of the funded address, like the fingerprint is the same, the length is the same. Check whether it's actually the same address. Then just end the script, because then you actually have the practically impossible case that you actually found an address. Or maybe somebody in case somebody uses the first private key, then I'm certain there's a lot of these sort of scripts running that will quickly find that. So never use like a private key which is like so bad. Like if you use the number 1000 as private key, even if the base 58 version of the private key looks like any other private key to a human eye, these like low Kolmogorov complexity keys are not safe, because you have this sort of websites that actually look up of whether or not there are funds on it, or you have this cheap script which does the same thing, right? Okay, and so that's how it works. The last thing to be discussed is the function of the funded stream, address stream, right? So let's do it. So as I said, I mean, we could open now one of these files, but it's pretty huge. The format that these files have here is as follows. You have just 2 columns. The first one is address, and the second one is the fund. They are in this data set already ordered, so the largest amount of funds are at the top. I mean, as we can probably see here, let's actually see what is the biggest one. Let's set the funds to 10,000 Bitcoin, and let's run it again. Okay, let's break it here already. Come on. So stupid. Since I manage the recording software, it's a little bit difficult for me to press the keys right with the microphone in front. That's why you saw this amalgamation of characters here. Okay, so it looks that the richest Bitcoin address, so we see here the rich list, is, Jesus Christ, my God, it's this one, with like 7 million Bitcoin or so, 3.5. When I downloaded the file that I use here, this was already 2 weeks ago or so. So let's see. It's probably a exchange address. Let's actually look up how much there is now. 141 was there 2 weeks ago. Let's check it out now. No, it's the same thing, roughly. Oh yeah, this has actually not moved. It's some cold wallet probably. Because as I said, I downloaded it or so, this file 2 weeks ago, but it doesn't seem there has been much going on since then. There was just stuff added to it. I mean, there's also web pages where it says some like the big exchange addresses are also known. There's known that they belong to the addresses to the exchange. Okay, but that was just an aside. Let's go back to the code. Let me set this to some nice things, just so I can upload it. As always, you find the script below in the gist. So this is the format, as I said, address funds, and what this function does is a small function within a function. It takes a raw row and it splits it where the separator is a tab, as you see here, and then the first entry is the address and the second entry is the funds, and then I convert it because the funds are given in sets, and then I divide it by 10 to the power of 8, and then you get the Bitcoin as a float. So for example, if I print the raw line here, okay, this is now printing while it loads. So if I run this again, Jesus, then you see here before I print it out. So this is okay. This is always one loaded address. So this is an address with 99 Bitcoin. Then this is the format as you see here, as a byte string, as it is in the CSV file, and I just split it into two parts and parse out the Bitcoin. So these are the 99 Bitcoins. I've got 99 Bitcoins, but okay. And this is the address, right? And it converts it to just a regular string. Okay, let's comment this out here. Let's make it nice. Okay, and so okay, I define the file path. This is given in the configuration as you saw before, right? The relative path and the file name. The relative path will depend on your setup. The file name need not. And then I use this zip to open the file. This is the file, right? And what I do is I don't load it into, like, this is the thing. I don't load it into a handle that I use in the rest of the script, but instead I create a stream which has all these values, right? So here I loop through all the rows. This is the first row, and so on and so forth. And in the end, I just take the funded address and add it to the stream. I've discussed streams, Python streams before in some detail in these videos, okay? If you're interested in that, it's a Python feature. Okay, the first row, however, says address balance. Okay, this is not a Bitcoin address or balance. It just says these words. So we have to skip the very first row of this file. That's what I do here. Then I load the line as string and as a float, as with this function, custom function there. I break the stream. The stream is like over once the fund is below a certain value which I have in the config. This only works because the file nicely comes ordered. Then I by the way, if for some reason you have actually use for the script, then it would be clever to actually create a file, for example, a file which just has the fingerprints. That might speed things up a tiny bit, I suppose. And okay, every now and then, no, exactly. If there's a flag there that here that you print out stuff. So if you want to print out every now and then this information, you can do it as well. This is what I do at the beginning, right? This is what you see here. This is exactly this printing statement here, which implement as a flag because when I load the second time, I don't want to see it anymore upon after the fingerprint, right? Okay, and then I yield the funded address because I know it's an address which has some funds. Yeah, and that's pretty much it. Similar to what we had in the previous scripts in the last 2 weeks, where I ran through secrets to generate addresses. I do this here as well. The only difference is the inclusion of this nice CSV file to actually look at properties of actually funded addresses. So this script involves funded addresses. Okay, I will leave it at that. If you are like, I think they were more or less popular, these sort of videos. I don't really plan to do much more on the elliptic curve private key from the Bitcoin blockchain, or any blockchain for that matter. However, I have a project planned regarding decentralized anonymous voting, which lends itself also to an implementation on a blockchain, which I will talk about, but there might be some weeks before I make the first video on that. Let me know if it interests you. I mean, I will do it anyway, but let me know nonetheless if you want to know about anything else. And with that, I say have a nice Sunday evening. Take care.